And now one last thing I wanted to point out about the algebraic aspects of inverse functions before we start talking about some trig. So like I said in the last video, the inverse function, when it exists, flips the role of x and y. So what that means is that if the point x comma y is on the graph of the function f, so if f of x equals y, then the reversed point y comma x is on the graph of f inverse, because now f inverse y is equal to x. Okay, so we can think about x ascending, or f rather, sending an x to a y, and then f inverse as sending the y back to x. Or vice versa, f inverse will send a y to x, and then f will send that x back to y. Therefore, when we think about domains and ranges, the domain of a function is going to be the range of its inverse and vice versa. So the domain of f is the range of f inverse. So the domain, remember, is a set of all allowable x's, but then the set of x's on the graph. That's the set of y's on the graph of the inverse function. The domain of f inverse, the set of all the x's on the graph of f inverse, is equal to the range of f of x, the set of all the y's on f of x. So when you go from f to f inverse or vice versa, you flip the roles of x and y. Okay, so now let's talk about our first inverse trig function, the so-called inverse sine, or sometimes called the arc sine. So we're going to start by thinking about the function sine x. Okay, and we begin by graphing it. Okay, so if we take a look at this graph, we notice that we run into a problem right away. Okay, and that is the function sine x is very definitely not one-to-one. So I said in the last video that for a function to have an inverse, it needs to be one-to-one. It has to pass the horizontal line test. Well, for the sine function, there are all sorts of horizontal lines, basically any horizontal line between y equals -1 and y equals 1, that's going to cross the graph in infinitely many places. So this is very much not one-to-one. So in order to define what we'll call the inverse sine function, what we're going to have to do is, just like with the example of x squared in the last video, we're going to have to restrict the domain to make it one-to-one. Okay, so what we will do is only look at the part of the sine graph that runs from x equals -pi/2 to x equals +pi/2. Okay, so when we do that and we ignore everything else, we get a function that is now one-to-one. So this graph does pass the horizontal line test. And it contains the entire range of the sine functions. That's another important thing because we want all the outputs of the sine to be included, and here we do get everything from y equals -1 to y equals 1. Okay, so what we're going to do here is not just look at f of x equals sine x, but restrict the domain to x between -pi/2 and +pi/2. Okay, so when we do that, then we can define what we'll call the inverse sine or the arc sine. So now f inverse of x, we're going to call sine to the -1 of x, or this is sometimes called, I don't tend to use this, but you'll see this from time to time in other sources, arc sine of x. Okay, so this is the inverse sine or arc sine. Okay, and what is the graph of this inverse sine going to look like? So remember, we can get the graph of the inverse function by reflecting the graph of our function here across the line y equals x. Okay, or probably a better way to think about it is to just flip the x's and y's. So we have 3 points here that are obviously on the graph of sine x with this restricted domain. We have a point at negative pi over 2, negative 1. Well, if we flip the x's and y's, that's going to go to the point x equals negative 1, y equals negative pi over 2. Okay, so we're going to have a point there. Notice that this sine graph goes through the origin, goes to the point 0, 0. Therefore, our inverse sine graph also goes through 0, 0. Okay, and then finally, there's a point at pi over 2, comma 1. If we flip the x's and y's, that gives us a point at 1, comma, positive pi over 2. Okay, and then if we connect those, and sort of take that graph and reflect it across the line y equals x, you're going to get a graph that looks like this. Okay, so this is the graph of the inverse sine function. Okay, now this graph is not terribly important, but the things that we can get from this graph are. Okay, so what are the properties we're going to have of the inverse sine? Okay, first off, we can look at the domain and range. So we're going to look at y equals the inverse sine of x. We see that its domain is negative 1 to 1. Yeah, the x values go from negative 1 to 1. That's the same as the range of the sine function. Okay, so that makes sense, like I said at the beginning of this video. Domain of the inverse function is the same as the range of the original function. And the range of the inverse sine is negative pi over 2 to positive pi over 2. Okay, and this is going to be the same as the domain of our restricted domain sine function. So the one where I just made it 1 to 1 by tracing over in pink and then erased everything else so that the graph was 1 to 1. So our y values for the sine, inverse sine rather, will go from negative pi over 2 to pi over 2. Okay, so what does that mean? Well, if we think about what the sine function does, the sine function is going to input an angle and output the sine, okay, which is a number between negative 1 and 1. Okay, so what the inverse sine does is inputs a number, which is going to reverse what the sine function does. So it's going to input a number between negative 1 and 1, and it's going to output an angle between negative pi over 2 and pi over 2, such that the input number is its sine. Okay, so whenever we are computing inverse sines, we can think about it this way. So if we're finding the inverse sine of some number x, that's going to be some angle theta. Okay, where theta is an angle between negative pi over 2 and positive pi over 2. And the sine of theta is equal to x. Okay, so let's do an example with some actual numbers. That will hopefully help us understand what we're doing here. Okay, but if you remember this definition for the inverse sine, then it really comes down to just being able to find sine values of some of our common angles. So let's say, for example, we wanted to find the inverse sine of negative square root of 3 over 2. Okay, so based on our definition, that's going to be some angle theta. Theta's got to be between negative pi over 2 and positive pi over 2. Okay, so that means that our angle has to be somewhere in the fourth of the first quadrant, and the sine of theta is negative square root of 3 over 2. Because, again, the sine value of our output has to be the input of the inverse sine. Okay, so since the sine of theta is negative, that tells us we have to be in the fourth quadrant. Since the sine is negative square root of 3 over 2, that tells us our reference angle is pi over 3. Okay, therefore, theta has to be negative pi over 3. Okay, and therefore, the inverse sine of negative square root of 3 over 2 is negative pi over 3. So that is the unique angle between negative pi over 2 and positive pi over 2, whose sine value is negative square root of 3 over 2. Okay, so one last thing I want you to note. There are all sorts of different angles that have a sine value of negative square root of 3 over 2, right? So for example, 5 pi over 3. So 5 pi over 3 is actually coterminal with pi over 3, or even 4 pi over 3, which would be in the third quadrant. None of those angles are the inverse sine of negative square root of 3 over 2 because they don't meet this first criteria. So for example, theta equals, if we did 5 pi over 3 instead, so if we went with a positive angle, this is not in the range of the inverse sine. Okay, because it is not between negative pi over 2 and positive pi over 2. Okay, so this is why it's important to make sure you understand that coterminal angles are not equal, they just have the same terminal side. So in this case, our angle would be negative pi over 3, because that's the only angle with the given sine value that's in our range of negative pi over 2 to pi over 2. Okay, so that's going to be all for the inverse sine. I will flesh this out with some Zoom sessions to come. Next, I'll talk about the inverse cosine and the inverse tangent.